All right, let's talk about something that trips up pretty much everyone when they first jump into Kubernetes. What in the world happens to your data when a container disappears? We are diving deep into persistent storage, and I promise, by the end of this, you'll get exactly how Kubernetes pulls it off.
Hey everyone, and welcome to DevOps Corner. If you get a kick out of deep dives into tech topics just like this one, do us a huge favor and hit that subscribe button and give this explainer a like. It really is the best way to support what we do here.
So, picture this. You've just deployed your brand new database inside a Kubernetes pod. Everything's running smooth. But then, for whatever reason, the pod restarts. Maybe it crashed. Maybe Kubernetes just moved it to a new node. You check your app and poof, your data is just gone, vanished into thin air. So what on earth happened?
Well, what happened is that out of the box, a pod storage is what we call ephemeral. It's temporary. It's tied directly to the life of that one single pod. So when the pod dies, all of its storage goes right down with it. Now, for anything that needs to remember things, like a database or really any app that saves files, this is a total deal breaker. We need our storage to live on, completely separate from any single pod's lifecycle.
Now, the way Kubernetes solves this is, honestly, it's pretty brilliant. It's all about separating the work. It splits the problem into two jobs for two key players. You've got the cluster administrator who manages all the real storage hardware, and then you've got the developer who just needs a place to put their data.
So let's start with the admin. Their job is to provision storage using an object called a persistent volume, or PV for short. Just think of a PV as a block of storage that's been made available to the entire cluster. It's a cluster resource just like CPU or RAM. This PV points to some kind of real storage, whether that's a cloud disk on AWS, a network share, or even just a folder on one of the nodes.
Okay, now for the developer. They don't mess with the PVs directly. Nope. Instead, they create what's called a persistent volume claim, or a PVC. And it's exactly what it sounds like. It's a request, a claim, for some of that storage. It's the same idea as a pod requesting CPU and memory from a node. A PVC requests a chunk of storage from that pool of persistent volumes the admin set up.
This right here, this slide, it captures the whole relationship perfectly. It's simple supply and demand. The persistent volume, the PV, is the supply of storage. The admin provides it, and it exists across the whole cluster. The persistent volume claim, the PVC, is the demand. The developer requests it, and it lives inside their specific project namespace. This abstraction, this split, is the absolute key to this whole system.
And this quote from Tech World with Nana just hits the nail on the head. It perfectly sums up why this is so great for developers. As a user, you don't care if the storage is coming from Google Cloud or a server rack in the basement. You just need, say, 50 gigs for your database or 10 gigs for your app. That's it. You just make a claim, and you let Kubernetes figure out the details.
So we have these two pieces of the puzzle. But how do they actually click together? How does a developer's request get turned into real, usable storage? Let's walk through the lifecycle and see how it all connects.
It all happens in 4 main stages. First up is provisioning. An admin can pre-create a bunch of PVs, kind of like stocking a shelf. Or, and this is super common, they can be created on the fly using something called a storage class. Next is binding. When a developer submits that PVC, Kubernetes goes looking for a PV that fits the request and binds them together. Think of it like a reservation. It's now a one-to-one mapping. Third, using. The pod simply refers to the PVC by name, and Kubernetes mounts the storage for it. And finally, reclaiming. When you're done and delete the PVC is released. What happens to the data then depends on its reclaim policy. It could be kept, deleted forever, or wiped clean for the next user. Now, a really important part of any claim is the access mode. It basically defines the rules for how that storage can be used. For a database, you'd almost always use read-write once because you only want one thing writing to it at a time. But for something like a shared file asset folder, you might need read-write many, so lots of pods can read and write to the same place. The trick is, the PV and the PVC have to support the same access mode for them to bind successfully.
Okay, that's enough theory. Theory's great, but let's see what this actually looks like in practice. Let's get our hands dirty and look at the YAML.
First things first, let's put on our admin hat. Our job is to create that supply of storage by defining a persistent volume.
Okay, let's break this down. In the specs section, the admin defines the capacity. Here, it's 5 gigabytes. The access modes it can handle, and the actual physical storage behind it. In this case, we're using host path, which is really just a directory on the node itself. Super simple for testing, but you probably wouldn't use this in production. And notice the storage class name is set to manual. That just means we have to create this PV by hand before it can be used.
All right, admin's job is done for now. Let's switch hats and become the developer. We need to make our demand for that storage by creating a persistent volume claim.
Now look at this. See how the developer's claim lines up with the volume. It's asking for the same access modes, read, write once. It's requesting a storage amount that fits within the PV's capacity. And it's asking for the exact same storage class name, manual. Because all of these things match, Kubernetes sees this and automatically binds this claim to that my PV we just created. It's a perfect match.
So we have the supply, we have the demand, and they're bound together. The very last step is to actually plug this into our application, and we do that right inside the pod's definition.
And right here, this is the secret sauce. Look really closely. In the pod's volume section, we're not pointing to the PV. We're not pointing to the physical storage at all. We are only referencing the claim by its name, my PVC. This is what makes the whole thing so incredibly portable. You can take this exact pod file to any Kubernetes cluster in the world, and as long as that cluster can satisfy the myPVC claim, it'll just work. It doesn't matter if the storage is from Amazon, Google, or a server under your desk.
Okay, so let's zoom out one last time and tie this all together. After seeing all these moving parts, what's the big idea? Why does this whole system even matter?
It all comes down to this one powerful idea, decoupling. For the admins, it means they can manage the what and where of the storage infrastructure without having to worry about every single app's needs. For developers, it means they can easily ask for how much storage they need on demand without being an expert on the hardware. And for our applications, this is the big one. We get true portability. Our application code can run on any cluster that knows how to fulfill its storage request.
And that's our look at persistent volumes and claims. Thanks so much for joining us at DevOps Corner. If this helped clear things up for you, please go ahead and like, share, and of course, subscribe for more deep dives.
So I'll leave you with one last question to chew on. Now that you know how to make your data survive a pod restart, what's the next logical step? How do you protect that data from being lost completely? How are you going to manage backing it up? Something to think about for next time. We'll see you in the next one.